Did everyone get one of these tables? We're good? Okay. So today we are going to cover chapter 9, which is all about hypothesis tests and confidence intervals, but we are dealing with numeric variables. And it involves the use of the t-table. Okay? So first I want us to learn how to use the t-table. Yes? Turn it up. Okay, is this better? Alright. Okay, so everyone's got one of these? Okay, so when you use the t-table, you might be asked to find the tail area of a t-score. Okay, so t-score is similar to a z-score, but it involves using the t-table. And so you might be asked to find the tail area. The use of the t-table is different from the z-table in that you're given what we call critical values and degrees of freedom. Okay? So for a given number of degrees of freedom, the t-table gives us certain values. So let's say we have 5 degrees of freedom. Okay? So 5df. Alright? This is chapter 9, but right now we're just using this table. So everybody should have their table in front of them. And when you look at 5 degrees of freedom, you will see in that row, you see the numbers 1.476, 2.015, 2.571, and so on, 3.365. And at the top of each column, you see something like t.100, t.050, t.025, and t.010. Do you see that?
Isn't it 0.001?
No, he didn't go all the way to the end.
I didn't go all the way to the end. I only copied the first 4 columns. Okay, and so what this means is that imagine a unimodal and symmetric distribution. So it looks a lot like the normal distribution, but it's not quite the normal distribution. It's the t-distribution. When it has 5 degrees of freedom, it looks something like this. If I were to draw a vertical line at 0 and shade everything to the right, how much would I have shaded?
50%.
0.5. That's correct. Okay. What the t-table says is that if I draw a vertical line at 1.476 and I shade everything to the right, the amount that I have shaded is equal to 0.100. Is that okay? And it says, if I go further away from 0, if I go all the way up to 2.015, and I shade everything to the right, how much do I have shaded in this tail?
0.050.
0.050. Is that okay with everyone? And so what we see is that as we go further away from 0, so as our numbers get larger, the amount that we have shaded in the tail gets what? Gets smaller. Okay, so this is a common question that students ask. Why are the numbers getting smaller when the other numbers are getting bigger? It's because we're getting further away from 0, so the amount in the tail gets smaller. Okay? Alright, so this is helpful if our t values ended up exactly at 1.476 or at exactly 2.015. If my t-score is exactly 2.015, I know that the area in my tail is exactly 0.050. But if the amount in my tail, let's say my t-score is equal to 1.7. How much do I have in my tail? Can you tell me? Well, the answer is you cannot give me an exact value. So we do know that the amount in the tail is going to be more than what number and less than what number. So the amount in my tail is what?
More than 20.
Okay, so listen to yourself saying that. It should be more than 0.05. Okay, so the amount in my tail is more than 0.05, but is less than 0.100. Can we see that? So, here's my t distribution, and we said that if I draw a line at 1.476, the amount in my tail is 10%, and if I draw a line at 2.015, the amount in my tail is 5%. So if I draw a line in between at 1.7, I know that I have more than, right here I have 5%, 050. But over here, if I shade everything to the right, I have 10%. So if I draw a line at 1.7, the amount in my tail is going to be between 5 and 10%. So tail area is between 0.050 and 0.100. And we're just looking at the column headings. We'll see that 1.7 is in between here, so my tail has to be in between these two. Yes?
If this was a quiz question, for example, would you want us to write the full sentence out, or can we just write what's above it?
Yeah, this is probably better.
So there isn't like an actual number answer to that question. Like for example, we can actually find out what is the t-score to 1.7. The only thing we
The
can
tail
say is-
area.
I'm sorry.
The tail area.
I'm sorry. The tail area. So the
So
answer-
if you're given only a table, the most precise you can give me is between 0.05 and 0.10. Okay? If you have a computer or something, you can get an exact value.
Cool.
But with the table, this is
So on the test, that's what you want us to do.
yes. Okay. Is that okay? So let's just try a few practice drills to make sure we know how to use the t-table. Is that okay? But is this concept okay with it? All right, so let's say I have 5 degrees of freedom, and my t-score is 2.9. 5 degrees of freedom, t is equal to 2.9. How much is in my tail area? Okay, those of you guys who came in late, I got tables that you will need. Okay, so the tail area for this problem is what?
Before that.
Between 1% and 2.5.
So the tail is between 0.01 and 0.025. Okay? And if you want to write it in the shorthand form, which I recommend, and make sure your less than or greater than signs are pointing the same direction, okay, or the correct direction. You can write it the other way. This is also fine, but your less than or greater than signs need to be pointing in the correct direction. So any of these forms is correct.
Can we do one more example?
Yes, of course. Are there questions on this though, before I go on?
I don't really understand where to find it.
I'm sorry?
I don't really know where to find it. So first you go there.
So first you look, so you're gonna have to figure your degrees of freedom, but I'm telling you, we have 5 degrees of freedom.
And that's here.
So you go in the row, right, that under the DF column says 5. And then you look at those numbers in that row, and you see, where is my t-score of 2.9? And we see that 2.9 is in between 2.571 and 3.365. Okay. So 2.9 is in between these two numbers.
Yeah.
So that means the tail area has to be in between the two numbers at the column headings.
T-score, is it with the star also like T-score?
No,
Just T.
the star has is for a critical value, so we're not going to worry about the star in this case. Sometimes
So
there's
it's just T equals to.
yeah, t is equal to 2.9. We can see. Okay, and so our tail is between 0.01 and 0.025. Is that okay? All right. Let's say we don't have 5 degrees of freedom, but let's say we have 15 degrees of freedom and your tail area is, or your t-score is 3.9. How much do you have in your tail? Do we have an answer?
Yes.
And what is our answer?
0.1 less than tail.
Not 0.1 is less than the,
I'm sorry, 0.001.
not 0.001 is less than the tail.
No, it's less than.
0.001 is greater than the tail, or that the tail is less than 0.001. Okay. So, if you look at the row 15 degrees of freedom, we see that the largest number in that row is 3.733, and that corresponds to t.001. Everyone can see that, right? 3.9 is beyond 3.733. And so we are farther away from 0, so does that mean we have more or less in the tail than 0.001? Yeah, so our tail has less than 0.001. Okay. So that's important. If you say the tail is greater than 0.001, that's wrong. The t-table is symmetric. So if you have a negative number, if I ask how much is in the tail for negative 3.9, you would just ignore the negative sign and look up the positive version. There was a question over here?
Yeah, which one is, so it's 0.001 last, the tail of last 0.001. I can't understand which one is right.
These are both correct.
They're both correct.
They're both correct. This one says the tail is smaller than 0.001, and this one says the tail is smaller than, or actually this one says 0.001 is greater than the tail, and this says the tail is less than 0.001. They're both saying the exact same thing. Okay. Again, the t-table is symmetric, so if you get a negative t-score, you can just look up the positive one, and the area for the tail is correct. Sometimes you will not have your exact degrees of freedom. So sometimes your exact df is not in the table. In those cases, always round down to the value you can find in the table. So if you have 57 degrees of freedom, okay, 57 degrees of freedom is not in the table, so you will round down and use 50 degrees of freedom. And that's only because our table is limited. If you had a fancier table with more entries for every single degree of freedom, you can use the exact 57 degrees of freedom. But in our case, we're limited.
Even if I have like 59, it's still
Always round down.
What's infinity sign on the bottom?
The infinity is if you have infinity degrees of freedom. You will not use, generally you will not use infinity degrees of freedom, but it's there. The infinity degrees of freedom is actually the same as the z-table. Okay. When the t distribution has infinity degrees of freedom, it becomes the z-table. And those numbers down there should look kind of familiar. They are the numbers that correspond to your critical values for a confidence interval. So if you remember, I said for a 95% confidence interval, you would use 1.96. For a 90% confidence interval, you use 1.645. Those numbers appear as infinity degrees of freedom. Okay, is that all right? Yes.
This is a DF standard.
DF stands for degrees of freedom. Degrees of freedom. Okay, so let's try one more. Let's say you have 36 degrees of freedom, and your t is equal to negative 0.8. How much is in your tail? So what is our answer? The tail is greater than 0.100. That's correct. Okay, so you would use 30 degrees of freedom. And when we look at 30 degrees of freedom, the first number we see is 1.310, and that corresponds to t with 0.100. Okay. But we see that 0.8, even though we have negative, we just ignore the negative. And we see that 0.8 is less than 1.310. So that means in our picture, we have 0. At 1.310, I have 10% in my tail. I'm drawing a line at 0.8, so I'm closer to 0, so the amount in my tail is going to be more than 0.1. So my tail area is greater than 0.100. Are we comfortable with the use of the t-table there? I hope. Okay, question?
Sorry, I was having a hard time understanding why it's greater than. Because isn't the number that you get, isn't the tail less than that number? Than 0.100?
Okay, so, okay. So, do you see my picture here? Okay. If I drew a line at 0 and I shade everything to the right, how much do I have shaded? Everything adds up to. Okay, so if I shade everything to the right of 0, I would have 0.5. Okay. What the table says is that if I shade everything to the right of 1.310, the amount in my tail is going to be 0.1. That's what the table says. And if you look at the next number for 30 degrees of freedom, it says if I go to 1.697 and I shade everything to the right of 1.697, how much would I have in my tail? Yeah, I would have 0.050. So here I'm drawing a line at 0.8. So right here, if I shade everything to the right, I have 0.1. If I shade everything to the right of 0.8, how much do I have? So it's not in the table, so, okay. What I do know is that right here, I shade everything to the right, I have 0.1. That's what the table says.
Right. Oh, so
When I look at 0.8, I don't, it's not in the table, but I do know it's going to be more than 0.1. But it's less than what? Less than 1/2 also. Okay. But it's always assumed that it's less than 1/2, so, I mean, we could write that the tail is less than 0.5, but that is always assumed. So we often just leave it off. Okay. But we could write that if we wanted to. Is that cleared up? Okay, is everyone okay? It seems like we're all okay. Well, anyway, I just wanted to make sure that's okay because we are going to use the t-table quite thoroughly in today's chapter. Okay, so we are dealing with chapter 9, and everything in chapter 9 deals with numeric variables. So we're doing inference for numeric variables, so that is confidence intervals. And hypothesis tests. And we will deal both with one sample or two samples. So last week we had chapter 8, and that was all categorical variables. This week it's all numeric variables. And a large portion of your final exam is going to be based on chapters 8 to chapters 9. So I'm just letting you know. There's no surprises. Okay. So let's talk about confidence interval. And in this case, we've got a numeric variable and one sample. So here we are making a confidence interval for the population mean mu. So before I get into how to make a confidence interval, why do we want to make a confidence interval in the first place? What's the idea here? Yeah.
To try to get a specific number around subject, or like to get a sample of the population and see how closely that can relate to the whole population.
Okay, so when we are making a confidence interval, what we are trying to do is we are trying to estimate a value of the population. So in chapter 8, we had categorical variables. So the thing we were trying to estimate was the proportion. So the population has a certain proportion. Maybe it's 20% of the population. Candy is red candies. So the population has a certain proportion. But we don't know that value. So we take a random sample and we see how much shows up in our sample. So maybe 18% of a handful of candies are red. Based on that 18% we see, we are creating an estimate for the population. So we say, I think the population is 18% red, give or take 3 or 4%. And we figured that out. We're doing the same thing here. We are taking a sample, and based on our sample, we're making an estimate for mu. And we say, based on my sample, I think the mean of the population is some number, give or take something else. So maybe we take a random sample, of 50 potatoes. And we weigh all 50 potatoes. The average weight is 280 grams. Or the standard deviation of 40 grams. I'm making these numbers up. Alright. So we've taken a random sample of 50 potatoes, and the average weight of that sample is 280 grams, and there's a standard deviation of 40 grams in that sample. So based on what we see here, what can we say about the population? What can we say the mean of the population. So right now, what would our best estimate of the mean of the population be? What?
The average weight of a potato is 280 grams, we can take 40 grams.
Yeah, so we would say, my guess for the average weight of all potatoes is around 280 grams, give or take, and then it's some value. Not going to be 40 grams, but give or take some value. Okay, so we'd say, you know, my estimate for the average weight of all potatoes is 280 grams, give or take something, okay? So what is how do we get that give or take value? Okay, well, let's make a confidence interval from mu. So here's the confidence interval for mu based on one sample. So we have x bar plus or minus t star times s over the square root of n. Okay. X bar, this is the center of the interval. T star is our critical value. And s over the square root of n is our standard error. What is x bar?
Center of the interval.
The center of the interval is our sample mean. So in this case, x bar is what number? 280. Okay, we'll talk about t star in a moment. What is s?
Sample.
S is the standard deviation of our sample.
40.
Sample standard deviation. S is 40. What is n? Sample size. So we would put square root of 50. So I put in all the numbers that we have except for t star. Okay. So to get t star, we would go to our t table and we would look at how many degrees of freedom we have. So the degrees of freedom for one sample is n minus 1. So how many degrees of freedom do I have?
49.
I have 49 degrees of freedom. Okay. When we go to our table, do we have 49 degrees of freedom? No, so I would use what? 40 degrees of freedom. So we use 40 degrees of freedom. Okay. And which value would we use? That depends on what confidence level. So let's say we are making a 95% confidence interval. So if we were making a 95% confidence interval, we would look at the column that says confidence level 95%, and I would go to the row that says 40 degrees of freedom.
2.021.
And so the number I would use is 2.021. I just want to make sure everyone can find that number.
I just want to know, sorry, it's kind of a, so, what number are we trying, like, okay, I get that we're using 40 DFs.
Yes.
But what number are we trying to find in that column?
So
You know what I mean?
the number that you are using depends on your confidence level.
Okay,
So let's say I want 95% confidence.
okay.
I would look at the very top, it says confidence level, and I would say 95%.
And you give us that confidence level, right?
Right.
Okay, got it, I got it.
So let's say say make a 95% confidence interval, and you have this information. So from this, you figure out you have 49 degrees of freedom. You don't see that, so you use 40 degrees of freedom. So you go to 40 degrees of freedom, 95% confidence. The number you use is 2.021. Is everyone okay with that? Any questions? Okay, so now that we have this, we can figure out our confidence interval. All right, so it's just a matter of punching this into your calculator.
91, 268.
So our confidence interval becomes 280 plus or minus, and I'm getting 11.4. So I get 291.4 and 268.6. I am 95% confident that the average or mean weight, average weight of all potatoes is between 268.6 and 291.4 grams. Is that okay? So what if someone asks, do we have evidence that the mean weight is different from 290 grams? What's our answer there?
No.
Our answer is no. We don't have evidence that it's different from 290. Why not?
In between those.
Because 290 is inside, 290 is within the interval. Okay. But if we said, do we have evidence that the mean weight of all potatoes is not 300 grams, we would say yes. 300 grams is outside of the interval. Yes, question? Do another example of this? Okay, we'll do a quick one, just because we have a lot to cover today.
Are we gonna get out early?
I'm sorry?
Are we gonna get out early? Yeah, 'cause it's raining.
I don't know. I can promise that. Actually, I don't want to do another example, just because we've got so much to cover, okay? We'll keep going, and then if we have time, we can do multiple examples of stuff. Okay, so that's a confidence interval for mu, and you've seen this. All right, we're going to do a hypothesis test now. Or actually, let's do the confidence interval, but this time we are doing a confidence interval for 2 samples. Okay, again, we are still dealing with numeric variables. Everything today is numeric variables. On the final exam, you're going to have problems that deal with categorical variables and numeric variables. And when you're dealing with categorical variables, you use proportions. When you're dealing with numeric variables, you're dealing with means. It's very important that when you read a problem, you know the difference between a categorical variable and a numeric variable. If you cannot tell the difference between a categorical and a numeric variable, you will be in big trouble. And quite frankly, you probably do not deserve to pass. So, you have to know the difference between the two. Okay, so we're still dealing with numeric variables. But this time we have 2 samples. Okay, and we're going to make a confidence interval. Now we are talking about a confidence interval for the difference between the population means. Okay, so with 2 samples, we are making a confidence interval for mu1 minus mu2. This is the difference between the mean of population 1 and the mean of population 2. And you should say, when you have a problem for a confidence interval, you will need some information. Okay, so in the problem, you should identify what is sample 1, the mean of sample 1, x bar 1, standard deviation, S1, and the size, N1. Okay. And you will need sample 2, the mean, which will be x bar 2, the standard deviation, which is S2, and the size, N2. Okay. And of course, you also need your confidence level. So someone might ask, what is the difference between the average height of a male and the average height of a female? Fair question. So let's say we've gone out and gathered data. we surveyed or we measured the heights. Let's say 25 random males. The average height is 69.5 inches, and the standard deviation is 3 inches. And then we measure the heights